Good morning. Today, good morning. There is a lecture 2, analysis of columns and connections. Lecture 2 is expression for the crippling load with the both ends columns are pinned or hinged and all the three conditions. Here, the first derivation. The expression for the crippling load when both the ends of the columns are hinged. So consider a column with just buckles or bends due to the crippling load. So column is AB and has a length of small l with the uniform cross section area A, capital A. It is hinged on both the ends, that is at the A and at the B it is hinged. Then due to the crippling load, the column will deflect into a curved form, that is ACB. It will form a curved path as shown in this diagram. Consider any section at a distance of x from the end A. From A at a distance of x, we will consider a section. Here the section is C point. Let y equal to deflection, that is lateral displacement at this section. So here the total deflection is y. So here the moment, so it is a concavity, so the moment value will be negative. So what is the moment about point A? Here the force applied is P. So we are going to take moment about the C point. So at the C point, the P into y deflection. So force P is the force and the distance is the y. So minus P into y will be moment value. So at the point C. But moment is equal to, you know that already we have studied in the deflection EI d square y by dx square. So which will be equal to moment, that is minus P into y. So rearranging this, you will get EI d square y by dx square plus Py equal to 0. Now this is a partial differential equation. With the constant here is P by EI, here d square by. So this will be converted as dividing the whole equation divided by EI, you will get this. Now this is a partial differential equation. So for this partial differential equation, the solution is y equal to C1 cos x root of P by root of P by EI plus C2 sin x root of P by EI. So how this equation comes? You already know that in the maths you have studied the ordinary differential equation. So ordinary differential equation and partial differential equation, here it is an ordinary differential equation. The equation is this, and it is in the format d square y by dx square plus alpha square y equal to 0. Here alpha square is equal to P by AI, so alpha is equal to root of P by EA. You know that the solution for this partial, that is you will convert Pi and Ci value. So Ci and Pi, here the total equation will be C1 cos alpha x plus C2 sin alpha x. So in this case alpha is equal to root of P by EA and it will be substituted here. So with this you will get the solution. So next, to find out the constant C1 and C2, for that we have to apply the boundary conditions. So similar to the deflection equation, we will apply the same boundary condition. So at x is equal to A, y value is 0, and at B, so here the x value is 0 and here the x value is L. So at B, x is equal to L and y will be equal to 0. So in this case the C1 becomes 0, that is you are going to substitute y equal to 0 and x is equal to 0, you will get C1 equal to 0. Then here substituting the value x is equal to L and y equal to 0, that is y equal to 0 and x is equal to L, C2 value, so it will be equal to 0 equal to C2 sin L root of P by EA. In this equation it is clear that C2, either C2 will be 0 or sin this value will be 0. As C1 is equal to 0, surely C2 will have some value and it will not be equal to 0. Therefore sin L root P by EI should be equal to 0. So we can exclude this C2. So if this is equal to 0, that is sin theta equal to 0. Now what will be the value of theta? So in what are all the thetas sine theta will be 0. So it will be in sine 0, sine pi, sine 2 pi and sine 3 pi and so on. So 0 cannot be taken because it should not, so it is 0, so 0 angle cannot be taken. We can take as pi value to get the value. So L root of P by EI equal to pi. So rearranging this, P is equal to pi square EI by L square. So now this is the crippling equation, that is P is crippling load, and this is the Euler's equation for the column having bending with both the ends as hinged. So next derivation, expression for the crippling load when one end of the column is fixed and the other end is free. One end is fixed and the other end is free. So similar to the structure, we will consider at x distance the deflection is x, and here the maximum deflection is a. Here the moment value will be, so force is here and only this value, so for this type of beam the moment is positive. So at the point here, at the point C, the value is P into, so P into, so perpendicular distance is from B to C. So this is x and this is L. So this distance will be L minus, sorry, the perpendicular distance is A and here it is y. So P into perpendicular distance will be this one. You can see. So we are taking moment about this point. So this point will be A minus y. So this distance will be A minus y, because from this point to this point it is A and this is y, so this will be A minus y. So moment will be P into perpendicular distance into A minus y. So similar to the previous expression, we are equating this to EI d square y by dx square. So again substituting the moment value, which is equal to moment, and rearranging this, you will get EI d square y by dx square plus Py equal to Pa. In previous case you got constant as 0, but in this case you have a constant P into A. So d square y by dx square plus P by EI into y equal to P by EI into A. For this, the solution is y equal to C1 cos x root of P by EI, because there is also a constant, here is also a constant. So here additionally there will be plus A plus this A. So how the solution came, here is a subsequent substitution how the solution came here. That is the, sorry, substitution, the thing is here. The equation A can be written as this empirical equation alpha square is P by EI. So alpha equal to P by EI, root of P by EI, and here y is equal to C1 cos alpha x plus C2 sin alpha x plus alpha square into alpha divided by alpha square, which is nothing but 1 into 1 by alpha. So which is substituted as, here it is alpha. So totally the equation will be like this. So that equation is applied here. Then boundary condition to find out C1 and C2. Here at A, when x is equal to 0, y equal to 0. By substituting this, you will get C1 as minus A, C1 as minus A, and then at x equal to 0, y equal to 0. You can see here at x is equal to 0, dy by dx is equal to 0. Here dy by dx we have to find out. So dy by dx is equal to substituting this in this equation, finally C2 value will be 0. After that, the crippling load value root of P by E cannot be 0, that because C2 is 0. So in this equation, C1 is minus A and C2 equal to 0 after substituting. Here alpha value is equal to minus alpha cos L root of P by EI plus A. Rearranging this, then you will get cos L root of P by EI equal to 0. So in what cases cos value will be 0 at pi by 2, 3 pi by 2, 5 by 2, etc. So we are going to consider the least one, that is pi by 2. So L into root of P by EA equal to pi by 2. So rearranging this, root of P by EA equal to pi by 2L, and P is equal to root pi square EI by 4L square. So this is a crippling formula for the beam which have one end fixed and one end free. So similarly for the fixed end. So next derivation is for the column having both end fixed. Here the moment value will be minus P into Y. So same substitution, same thing. Here the solution for this equation will be y equal to C1 cos x root of P by EI plus C2 sin x root of P by E plus m naught by P. Here m naught is the initial moment in the fixed condition. M naught is the initial moment in the fixed condition. So m divided by P value. Then applying the boundary condition, here x is equal to 0, y equal to 0, at x is equal to L, y equal to L. So after substituting, we will get that C1 is equal to minus m naught by P, and then C2 is equal to 0, similar to the previous case. After substituting this, you will rearrange the conditions so that it will be 0, and finally cos L root P equal to m naught by P into P by n naught equal to 1. Here cos theta is equal to 1. Where the cos theta will be 0, it will be 1 at 0, 2 pi, 4 pi, etc. So for the least value we will take 2 pi. So here P is equal to pi square EI by, so here it will be 4 pi. Here there is a mistake, you will get 4 here. So it is 4 pi square E by L square. So this is a final derivation. So similarly for this derivation, the same process it will happen, and the same procedure, and finally it is 2 pi square EI by L square, 2 pi square L by E square. So these are the 4 equations which is applicable, and the 4 derivations for each conditions. Thank you.